In this video, we're going to go over the hydration of alkynes and also tautomerization. On the screen, we have 1-butene, and when we react it with water, we're going to have something similar to alkenes, where the nucleophile is going to attack that hydrogen from the water, and we're going to get a carbocation intermediate. So everything will stay the same, except where our triple bond is, which will now become a double bond. And we are going to put the hydrogen on the less substituted carbon so that we can put the plus charge on the more substituted carbon. The carbon on the left, where we have the double bond, has one alkyl group donating some electron density, whereas the carbon on the right doesn't. It only has the hydrogen. Since that's the less substituted one, that's where we're going to put the hydrogen, and we're going to put the positive charge on the carbon on the left. After this, we're going to get our hydroxide that we just formed being attracted to that plus charge, giving us a hydration product, very similar to what we saw in alkenes. So we have CH3, CH2. This carbon now gets the OH with our double bond and our newly added hydrogen as well. This will not be our final product, however. We are going to rearrange something called tautomerization, which is a simultaneous migration of a proton and double bond. Right now, we have what is called an enol, which is when we have a carbon-carbon double bond, and then we have an OH group attached to one of those carbons. This is not as stable as either an aldehyde or ketone, something with a carbonyl. A carbon-oxygen double bond is stronger than a carbon-carbon double bond, so that form will be more preferred. And what we're going to see is the hydrogen from the OH group going to the CH2 that's about to lose that pi bond. And what we'll see is first the unchanged part, and then the carbon that was with the OH is going to become a carbonyl group. We're going to get a single bond, and then that CH2 turns to a CH3. All that happened was the hydrogen did a hydride shift, and then at the same time we had our pi electrons shift to give us the carbonyl, which is more stable. This form that we now have, which is our final product, which I just boxed off, is our keto product. These two are isomers. The keto product is preferred rather than the enol product because the C double bond O is stronger than the carbon-carbon double bond. If you found this video helpful for understanding the mechanism for hydration of alkynes and tautomerization, please consider liking and subscribing, as it really helps the channel. And if you want to see more organic chemistry content, more mechanisms or examples, the playlist should be on your screen now. Thank you so much for watching.